All right, now we're going to look at specifics on how to actually induce an EMF and do some more specific problems. So if we have a uniform magnetic field, we can write the flux as B times A times cosine theta. And since there's three variables in that expression, there's really three ways to generate an EMF. We'll focus on two of them today because the changing the area case actually gets its own dedicated section. So first you can change B. So if you just alter the magnetic field strength, you'll induce an EMF. If you change the area, this is typically done by changing the effective area in systems similar to like a railgun or a conducting bar. That's known as motional EMF. That induces an EMF. And then also you can change the angle, which is how a lot of our power is actually generated, is by rotating conducting loops near magnets. So here's a visual of each. So you can change the magnetic field, so make it weaker or stronger. You could change the effective area, or you could change the angle the field makes with the loop. So first we'll do a few involving this just changing B. So we have a circular conducting loop of radius 0.4 meters. So that's given. The resistance 10 ohms given. It's in a region of magnetic field perpendicular to the plane of the loop. So again, this would just be a case where there's really no consideration of theta required because our magnetic field is just directly out of the loop like that. And I suppose I can draw it better than that. So it is increased out of the page via this quadratic expression, and all of our units work out. So first thing we want to do is calculate the magnetic flux through the loop at time t equals 3 seconds. So we just want to find the flux, and notice that everything is nice and perpendicular, so there's no theta involved here. So we can just write that the flux is just going to be equal to B times A. Because we have a constant magnetic field exactly perpendicular to an area A. And we said the magnetic field B is given by this 0.025 t squared times the area, which is pi times r squared. So don't forget the area. We're not just looking at the magnetic field, we're looking at the flux, so we have to incorporate that area term. So if we plug in the magnetic flux, if we plug in time equals 3 into that expression, using our known values of the radius of the circle, we will get approximately 0.113. And then this is definitely not a unit we have to memorize, but we can definitely think about what the unit of magnetic flux should be. So the magnetic field is measured in Tesla, and area is measured in square meters. So we should just get Tesla meter squared. All right, now we can calculate the magnitude of the induced EMF. So now we'll apply Faraday's law. So we know that the induced EMF is just equal to the rate of magnetic flux change. And we're almost always talking about magnitude here, so we drop that negative sign. The negative sign is just for Lenz's law. All right, now we'll just take a derivative of the magnetic flux, which is the derivative of BA. And notice the area isn't changing, so we don't have to deal with any product rule with this. We're just taking the rate that the magnetic field changes and multiplying by the area. So we're just taking the derivative of 0.025 t squared and multiplying by the area of pi r squared. Which would be equal to 0.05 t times pi r squared. And then all we have to do is evaluate this at t equals 3 seconds. So plugging in at 3 seconds, we just put in 3 for time, and we put in our usual radius of 0.4 meters squared, and we get 0.075 volts. All right. Indicate the direction of induced current flow in the loop at t equals 3 seconds. Well, again, here is a picture that will definitely help. So again, we have a magnetic field that's out of the page, sorry, out of the plane of the loop, and it's getting stronger. So as such, the induced current is going to generate a field that opposes the flux change. So generally how I do this is I figure out what kind of change in flux we have. So we have phi is getting more positive. So as such, if you're increasing in the positive direction, this means your delta phi would be positive if you're getting more of a positive quantity. And as such, we're going to need a clockwise current to oppose the flux change. And again, I know that because in general, these clockwise currents are creating negative contributions to flux. But again, we could just use the right-hand rule here. So if I look at my loop, right now I'm getting a change in flux that's positive. So as such, I need a clockwise current, and then if you wrap your right hand in the direction of this motion around the loop that the current is going, we do in fact see that there would be a magnetic field generated into the plane of that loop. All right, rate of energy dissipation at t equals 3 seconds. Well, there's a few expressions for power we have access to. Because again, power is the rate of energy dissipation. So I delta V is the definition. Or you could do some substituting with Ohm's law and come up with I squared R or delta V squared over R. And in our case, we haven't actually calculated the current, so it's probably the best decision for us to just use delta V squared over R, because we were given the resistance of the loop, and we did just find the EMF in the previous part. So we're just going to find the EMF induced at 3 seconds, square that, and divide by the resistance, which was 10 ohms. And doing that, we get a very small 5.4 times 10 to the minus 4 watts, which is a joule per second. So every second, so at t equals 3 seconds, there would be 5.6 joules per second being dissipated in that loop. All right, total energy dissipated over the entire time interval. So let's go back and see what that entire time interval was. Increases from 0 to 6 seconds before being held constant. So total energy dissipated. Well, if we know that power is the rate that energy is being dissipated, then this means the total energy dissipated is just going to be summing up all of those individual rates of dissipation. So if we integrate the power with respect to time, we do get our answer. So we're just going to integrate this expression for power. So I'm just going to integrate the induced EMF squared as a function of t. divided by R. And we're given that this is happening for 6 seconds. Our induced EMF as a function of time was equal to 0.05 t times pi r squared. And we have to square that whole thing and then divide by our resistance, which was 10 ohms. So again, this is quite a nasty expression, so I would definitely just type it in to a calculator at this point, because again, we do know that value of little r is 0.4 meters. So just plugging that in, we get 0.0045 joules. So again, not much EMF or energy kind of being dissipated in this process due to the very weak magnetic field. Suppose that after t equals 6, the magnetic field is fixed at its constant maximum value. So you could check that if I plugged in t equals 6 to the magnetic field expression, I would in fact get this value. Sketch a graph of the current in the loop versus time. So it's definitely easier just to think about what's happening with B, first of all. So what's happening with the magnetic field is the magnetic field is increasing quadratically. And then after t equals 6, it is held constant at some value. And also notice this would be the graph of magnetic flux through the loop as well, just scaled by some constant, because flux is just the B field times the area. So we know that current is the induced EMF divided by R. But also, because of Faraday's law, we know the induced EMF is given by the flux change. So this would just be 1 over R times the rate at which the magnetic flux is changing. So we're just looking for sort of a derivative of this magnetic field graph. So first we probably didn't need to go through all that to know that it was going to be 0 from 6 to 12 seconds, because if there's no changing field or area, there's no change in flux, so no current is induced because there's no EMF. But since our graph was proportional to r squared for the magnetic field, we know that its derivative must be a linear function. So the induced current is going to increase linearly before instantly dropping to 0 when it's held constant, because if there's no flux change, there is no current. Now suppose the original conducting loop was replaced with a loop with significantly more resistance. Describe how this change would affect the features of your graph. Well, what is resistance exactly doing here? Well, the resistance definitely doesn't affect the EMF induced, but it certainly affects the current. So we know that current is equal to the EMF divided by the resistance, right? That's just Ohm's law. So if the resistance increases, then that means the current has to decrease. So as such, the graph would just become shorter. In height. So you'd have a lesser slope. You'd have a lesser slope of your graph because your maximum current would be decreased. And there would be a linear relationship. All right, now for a symbolic one. A rectangular conducting loop of length L with W and resistance R is placed into a magnetic field given by this expression. It's some constant times the quantity t minus 2 directed into the plane of the loop. The magnetic field decreases in magnitude and then is constantly held at 0. So just to visualize what this looks like, we know that if I plug in 2 into this expression for B, it reaches 0, and we also know this is negative. So we have something that sort of looks like this. All right, first, magnetic flux as a function of time through this loop. Well, once again, it's entirely into the page, into the plane of the loop, so no theta considerations. So phi would once again just be the magnetic field times the area. And in this problem, the magnetic field was given by B0 times T minus 2 times the area, which would be L times W. So we get B0 LW times T minus 2. And we'll say magnitude of the magnetic flux, because sometimes it's not clearly defined what direction should be positive and negative. So we'll say magnitude. All right. Magnitude of the EMF induced. So now we just take the derivative. And we actually just have an expression for the magnetic flux already. So we're just taking the derivative of B0 LW times T minus 2. Well, this minus 2, this sort of shift term, isn't really doing anything because there's no T dependence. So B naught LW is actually just our constant EMF induced. Which should make sense, because if we have a linear function, that's derivative is a constant. So we should get a constant EMF. All right, current induced as a function of time. Well, current is just the EMF divided by the resistance. So we just divide our previous answer by the resistance of the loop. And indicate the direction of current flow. Well, once again, notice that in this case, we have this loop, and the magnetic field is getting weaker into the page. So the loop needs to generate a current to restore its negative flux, or its into the page flux. And that would be clockwise again. So this would be clockwise. Because if you wrap your right hand around the loop, you'd get your thumb pointing into the page. So because the into the page field is decreasing, the current has to work to restore this into the page B field. All right, derive an expression for the total energy dissipated within the loop. Well, we just said that energy could be found by integrating all of the power contributions. And the field is decreased over a 2-second interval. And we'll once again just use the EMF squared divided by R expression for power, which is typically your go-to for this one. We did have the current, so we could use any of them. So the EMF we said was equal to B0 LW all squared divided by R. And notice we actually didn't need all the integration because we had a constant EMF. So everything gets factored out of the integral. So we'd really just be generating a power of B naught LW all squared divided by R for 2 seconds. So we're just multiplying the power by 2. So we get 2 B0 LW all squared divided by R. Graph the magnetic flux through the loop on the interval 0 to t to 4 seconds. Label any intercepts. So we know that the field is decreased to 0. So always try to get your extremes right. So we also do have to define a direction here. So we're going to say out we're going to say out of page is equal to positive flux. But after 2 seconds, there's no magnetic field, so there's no magnetic flux. That was just given to us in the problem. It was also given to us that the magnetic field started at some negative value, because we were given into the page field here, and it decreased linearly in magnitude. So we just get this graph. And we have to find what the intercept is. So evaluating the flux at 0 would just be plugging in 0 into our magnetic field equation. And looking at our expression, we would get a negative 2 B0. So negative 2 B0 LW would be our intercept. Suppose the length of the loop was doubled, keeping the width and resistance constant, assuming the magnetic field still extends through the entire loop, a factor which the vertical and horizontal intercept will change. So first, the length was doubled. So we're looking at the graph of flux, which is the B field times the area. And well, if we're just doubling the length only, so not both dimensions, we're just doubling one dimension of the loop, well, we see that area is going to get multiplied by 2. So we're going to see what does that exactly do to each intercept. Well, for the vertical intercept, you're just going to have twice the initial magnetic flux, so that would be a times 2. And then the horizontal intercept, that's basically asking when the flux reaches 0. And in this case, even though we have a larger area, it was still being decreased to 0 in 2 seconds, so there's no change to the horizontal intercept. All right, now for a graphing question. A square conducting loop of side length 2 meters and resistance 100 ohms is subjected to a time-varying magnetic field perpendicular to the plane of the loop. So still no angle things to consider. Calculate the magnitude of the current at each of the following times. So again, the formulation is going to be the same for all of these parts. If we're finding the current, we need to have the EMF. So we definitely want to find the induced EMF in the loop and divide by resistance in each case. So the induced EMF will always just be given by the rate of flux change through the loop, which is going to be the rate of change of the magnetic field times the area. And since the area isn't changing, we're just looking at the rate of change of the magnetic field times the area. So we're really just looking for slope now, because we're looking at a graph, so we can interpret that as a slope. So notice in my first segment here, it took 1 second for the magnetic field to change by 0.36 Tesla. Then it's held constant for a while. And then it also takes 1 second to decrease by 0.36 Tesla again. So we're going to get equal currents as the field increases and decreases, and zero current when it's held constant. So in this case, our slope is 0.36 divided by 1, and our area, sorry, induced EMF, in our area, it is a square of side length 2 meters. So doing that allows us to get our EMF, and then we'll just divide by the current, or sorry, the resistance. So this is 1.44 volts. So then the current would be the EMF divided by the resistance, which is equal to 1.44 divided by 100. So just shift the decimal twice, and we get 0.144 amps. I used a lot of space here because we don't need to do a whole lot of work for the other two parts. T equals 1.5 seconds. Well, there is no change in magnetic field up here. So notice this is constant. So between 1 and 2 seconds, there is no change in magnetic field, so there's no change in flux. So there's no change in flux, so I equals 0. And then due to symmetry, at t equals 3 seconds, well, notice this is the exact same slope as before. So it's going to be 0.144 amps. The only difference would be the direction of the induced current, which would be reversed between the two parts. I didn't ask that due to ambiguity in the directions, but the induced current would change direction when it's decreasing versus when the field is decreasing versus increasing, but it is the same exact computation. All right. Solenoid with n turns per unit length is given a current I0 in each coil. First, we're going to find the direction of the magnetic field inside the solenoid. Well, I'm going to take my right hand. I'm going to point my fingers into the page where those X's are. And if I curl those fingers to come out of the page where the circles are, well, my thumb points left. So there's a constant field to the left inside the solenoid here, as we've learned before. So this would be left. To justify our answer, this would just be the right hand rule. We could elaborate a bit more, but for time purposes, I will not. So placing your fingers in the direction of the current flow, or sorry, curling your fingers in the direction of current flow would cause your thumb to point left. All right, starting from Ampere's law, we want to verify the formula for the field inside a solenoid. So I'll draw my little solenoid here. And again, here's one that kind of has a weird Amperian loop to draw. Again, we pick a loop that's partially in and out of the solenoid for this, because if we have a constant field inside and no field outside, this means that the only thing contributing to our magnetic circulation would be just the side of the rectangle that's horizontal aligned with the solenoid. So we're going to come up with some fake length parameter x that better cancel because it means nothing. So Ampere's law says that the magnetic circulation is equal to mu naught times the enclosed current. So our circulation is just Bx because we have a magnetic field B circulating for x, so just one side of the rectangle. Then mu naught times the enclosed current. Well, what's the enclosed current? I have n coils per unit length. So to find how many coils I've enclosed, I need to multiply by the length. So that's how many coils I have enclosed. And then I just multiply by the current. So I'm enclosing nx coils of I0 current. And notice the x's cancel, so we get the familiar B from the solenoid formula, mu naught little n I0. And not that it showed up here, but this little n is capital N divided by length. So now we'll apply this to induction. A small circular conducting loop of radius A and resistance R is placed in the loop, and the solenoid current is changed. So what we have is a magnetic field generated by the solenoid, but since the current in the solenoid will be decreasing, there's going to be some sort of EMF induced in this smaller circle. So indicate the direction of the magnetic field produced by the conducting loop. Well, we have a leftward magnetic field in the solenoid that's decreasing, so the current loop will attempt to restore the field to its former glory, so that will be left. And then derive an expression for the magnitude of the EMF induced. So the EMF is the flux change and once again our area is not changing, so we're taking the derivative of the magnetic field, which is mu naught little n times I of t, which is varying, times pi a squared for our little conducting loop here. And then everything is constant except for the current. So this would just be mu naught n times pi a squared times di dt. And looking at what di dt actually will be here, well, it's I0 e to the minus t over tau. So di dt would just be negative I0 over tau e to the minus t over tau, just doing the chain rule here. And we'll make that quantity positive just to be consistent with the magnitude here. So we're going to get a lot of symbols here. Mu naught n pi a squared times I0 over tau e to the minus t over tau. And that is a lot of unique symbols in here. Don't know if this is the record yet, but we have 1, 2, 3, 4, 5, 6, 7, 8 adjacent letters. Derive, but do not evaluate. Thank God we don't have to evaluate it. An integral expression which could be used to determine the total energy. So we know that energy, for the third time, is just the rate at which energy is dissipated, which we call power. So I am just going to integrate. And it says after a long time. So this would be after many, many taus. So we just assume that's infinite. And we're going to square this entire nasty expression. And divide by the resistance. That is absolutely diabolical. Oh, and I forgot my dt. That is an absolutely diabolical expression for power. Or sorry, the energy dissipated. Is this evaluatable? Oh yeah, yeah it is. I would definitely say it is, but not worth my time right now, I'd say. We'll say this is an exercise best left to the reader. All right, a conducting loop of length L with W and holding a bulb of resistance R is placed a very short perpendicular distance from a long wire. We'll see this question so many times, this setup of like a loop near a wire. So first, old stuff. Starting from Ampere's law, derive an expression for the magnitude and direction of the field caused by the wire. So again, if we have some sort of a wire like this, we had a magnetic field that circulated, not that way, that circulated counterclockwise. So we chose a circular Amperian loop. So we could just say that the line integral of the magnetic field, which we've been calling circulation, is equal to mu naught times the current enclosed. So we have a field of B circulating for 2 pi r, and then the current is just I. So we get, for the millionth time, our familiar formula for B from a wire, mu naught I for 2 pi r. Derive an expression for the total magnetic flux through the loop. So there's a very common incorrect answer here. This is a case where we can't just do flux is equal to B times LW. That's not true, because the B field changes. So if I stick my right thumb in the direction of current, my fingers would poke out of the page, above the wire, and into the page below. So this generates a field like this. So near the wire, it's going to generate a lot of field into the page, and then farther away from the wire, it's going to slowly decrease. So I can't just multiply B and A together. I need to actually take an integral. So instead, I'm going to integrate along horizontal strips. And find my flux that way. So to do that, you can imagine we have our little rectangle here. And since the flux will be constant along these little strips, we're going to slice horizontally, because it's vertically that our field is actually changing. So notice that from the figure here, our slice would have a horizontal length W and a vertical length dy. So that's going to be our area expression. So the magnetic field as a function of y would be mu naught I over 2 pi y. And then we multiply by the area, which would be just the width times dy. And now we have to think about our bounds. So the closest a slice could be to the wire is D, and the farthest a slice of the wire could be, or sorry, a slice of the loop could be from the wire is D plus L. So then factoring everything out, well, practically everything, we get mu naught IW over 2 pi times the integral from D to D plus L of dy over y, and that's just a natural log rule. And using the fact that subtracting the upper and lower limits inside a log is division, we would get mu naught IW over 2 pi ln of D plus L divided by D. You could simplify a bit further if you wanted to, but this will be fine for our purposes. You could also include a negative sign for this into the page field. So now suppose the current is decreased according to this expression, where I is some maximum value, and then it decreases until it reaches 0, indicate the direction of current flow within the loop. and derive an expression. So notice that what's happening in our loop is that in our loop, we would be getting less negative flux because all of our field is into the page here, and if you're decreasing the current, you're decreasing the amount of x's into that loop. So as such, we would need a counterclockwise current to oppose that. No, I lied. I completely lied. It is clockwise. Don't listen to me. Once again, we're restoring it to its former glory. Now we need an expression for the current as a function of time. So luckily we found what flux was. Flux was this absolutely nasty expression of mu naught I w over 2 pi natural log of d plus L over d. Luckily, the current as a function of time isn't too bad from this, because if we look, there's only one thing that's changing, and it's I. So the EMF would be the flux change. And I can actually bring everything out of this expression except for the one thing that's changing, which is the current. And notice that we're actually just having a linear decrease. So the current is just decreasing with a proportionality constant k here. So this means that this would be equal to k. And again, I'm just getting rid of all the minus signs just to make current and flux and EMF positive quantities. So the current would just be the EMF divided by the resistance, which would be mu naught W over 2 pi R times ln of d plus L over d times this constant k. All right, suppose the value of k is increased. Indicate how the brightness of the bulb would compare. Justify your choice. Well, based on this expression, we had a whole bunch of garbage times k. So the bulb is brighter in the new setup. Because we just said that current is proportional to k. And then as current increases, power increases. An easier way to see it if you didn't want to go through all this, because I know that I wouldn't want to do all this if I was just asking that conceptual question, is, well, k is the rate at which the current is decreasing. So if you're increasing the rate of current change, then you're increasing the flux change. So you're increasing the EMF and increasing the voltage and current. All right, and then to conclude, let's have one example of changing the angle. So a square loop of side length s is placed at rest within the xy plane. There's a uniform magnetic field pointing out of the plane of the loop. Explain why no EMF is generated if the loop is rotated on the z-axis. So I encourage you to sort of think about this and kind of mess with it live here. So if I have something just in the xy plane, and I spin it around a line perpendicular to that xy plane, the angle never changes. Because even if I This is just amounting to spinning it clockwise or counterclockwise. So if I just spin the loop sort of counterclockwise, like this, and I'm physically turning it, well, there's no difference in the amount of magnetic field penetrating that loop. So there's no change in theta. So that the flux change would be 0. But there would be an EMF if we rotate in any of the other two directions, because then we start to get the field actually rotating. So to do that, we're just going to write our general expression for magnetic flux, because now the angle matters. So flux would be B times A times cosine theta. And the loop is being rotated at a constant angular frequency omega, doesn't matter if it's the x or y, it just can't be the z. Assume it begins at rest in the xy plane. So, what this tells us is that this angular frequency omega, it tells us that we'll complete 2 pi, we'll go through an angle of 2 pi radians each second. So this just tells us that we can write our expression as b times a times cosine of omega t. Might have been a while since we saw this, but again, angular frequency just is the rate at which this angle is changing, so we can put it as omega t. What else do we know? It's a square of side length s. So we also know we can write this as bs squared cosine omega t. So then if we want the EMF, the magnitude of the EMF, we're just going to take the rate of flux change through the loop. And to do that, we're just going to take the derivative with respect to time, which would be bs squared times negative omega sine omega t. And after getting rid of the negative that we picked up from the chain rule, we'd get bs squared omega sine omega t. And lastly, we're going to do the same thing, except it's rotated at a constant frequency, not angular frequency. So the answer is actually the same. So the answer will be the same, where the EMF induced is going to be bs squared times omega sine omega t. But we just need to figure out what it is in terms of frequency. So there's this nice relationship that if omega is an angular frequency, and that represents the frequency in which you are performing an angle of 2 pi, we can write omega is 2 pi f. This is a fact, and it is worth knowing. This might be on the equation sheet. So bs squared times 2 pi f times sine of 2 pi ft. So these are the most common ways of writing a trig function that varies at a constant rate with its angle. So it's either omega t or 2 pi ft. So see which one you have. That's Faraday.